We're looking at problem 3 from the practice exam 3. So we're asked to determine if these three series converge or not. So the first one here, we'll decide first what we want to compare it to. So remember that the way we do that is we check for large n, what is this series looking like? So for large n plus 1 over n squared plus 2 is about the same as if we just ignore the constant terms, we get n over n squared, which is the same as 1 over n. So we're going to compare this thing to 1 over n, which we know is a divergent p-series. So let's note that. So 1 over n is a diverges p-series, p equal to 1. So knowing that, we'll be able to determine what our conclusion is when we do the test. So in this case, the limit comparison test would be most appropriate because we have plus signs in both the numerator and the denominator. So let's do that. Limit comparison test says that we want to find the limit as n approaches infinity of the series that we want to know about, which in this case is this one, divided by the series that we do know about, which is 1 over n. Since we're dividing, we'll just invert and multiply. So we'll get that, which then becomes n squared plus n in the numerator and n squared plus 2 in the denominator. The important thing here being that they both have the same power, and we know what happens when we take a limit to infinity when we've got the same powers. The limit is the ratio of the coefficients, which in this case is 1. And for a limit comparison test, all that matters is that that number is greater than 0, positive and finite, which it is. So that tells us that these two series, the one we're looking at and the one that we compared it to, they must do the same thing. And since the one that we compared it to, we know that diverges, this one must also diverge. So that is our conclusion. So the series that we're looking at diverges by limit comparison. For part B of number 3, we've got a series that has a fast growing term, 3 to the power of n. That's exponential growth, so that is the indication that we should probably use a ratio test. So let's do that. So ratio test requires us to find the limit of the n plus 1th term divided by the nth term, and that's the same as multiplying the n plus 1th term by the reciprocal of the nth term. So that's what our limit is going to look like. That's the limit we have to find. Technically, absolute value, we're not going to need those here, but we'll put them anyway. Okay, so let's rewrite that numerator term as 3 times 3 to the n. And then we'll just leave this one alone. Denominator, I'm not going to bother expanding that. We'll just leave it as n plus 1 to the 3rd plus 3. And then we've got our 3 to the n here. We can cancel that 3 to the n and that 3 to the n. This 3 is a constant, so we can pull it outside, out in front. So that leaves us with n to the 3rd plus 3 over n plus 1 to the 3rd plus 3. So this limit, without expanding that, we know that if we did expand this denominator, the leading term would be a n to the 3rd power. And that's all that matters when we're talking about a limit to infinity. Coefficient would be 1. Coefficient of the numerator is also 1. We also have a 3rd power there, meaning that this whole limit must be 1 multiplied by the 3 there. 3 being greater than 1 is what matters here. That's the conclusion for the ratio test that says that this thing must diverge. Okay, so ratio test for fast-growing terms. So looking at part C, we've got factorial growth in all over this one. So this is definitely ratio test. So we're going to take the limit as n goes to infinity of the n plus 1th term, so n plus 1 factorial. Replace that, you get 2 n plus 1 in parentheses, and then factorial applies to the whole thing. And then we've got, if I add 1 to that, I get n factorial. multiply this by the reciprocal of the nth term, so that's going to be 2n factorial n minus 1 factorial over n factorial. Okay, let's go ahead and expand that denominator. So we'll get, just repeat the numerator here, n plus 1 factorial, 2n factorial, n minus 1 factorial. Distributing the 2, we get 2n plus 2 factorial, n factorial, and then another n factorial. Okay, so now we need to rewrite these in such a way that so that some of these factorials are going to cancel out. N plus 1 factorial, we can rewrite that. So we'll get n plus 1 times n factorial. The n minus, or the 2n factorial, I think we'll just leave that one alone. And then the n minus 1 factorial, we'll leave that alone too. Okay, now in the denominator, let's write that as 2n plus 2 times 2n plus 1 times 2n factorial. So that's this, rewritten in that way. Still have the 2n factorials there. So now we can start canceling at least a few things here. That n factorial can maybe cancel with that one. We've got a 2n factorial can cancel with that one there. We have another n factorial here, so let's, I probably should have rewritten that. Let's go ahead and just do one more step here. Let's write, let's see what we've got left. We've got n plus 1 here, n minus 1 factorial, and then we've got these terms here. Let's go ahead and multiply that out. We'll get 4n squared plus 6n plus 2. And that's the only thing that's left. Let's go ahead and write that as n times n minus 1 factorial. That's the n factorial that was left there. And again, the reason we're doing that is because we saw that n minus 1 up there. I probably could have done that over here, but anyway, we got it. So looking at what we've got left, then we've got limit as n goes to infinity of what's left in the numerator, just n plus 1. What's left in the denominator, we've got 4n to the third plus 6n squared plus 2n. And I think it's pretty easy to see, higher power in the denominator here. This limit is 0. 0 is less than 1. So series converges by the ratio test. For part D, we need to notice that this is an alternating series. So we can use the alternating series test. That requires us to find the limit of the nth term. The nth term excluding this part of it. So that's the limit of this, 2n squared plus n plus 1. That limit is clearly 0, so that checks out. And then we also want to check if the n plus 1th term is less than the nth term. So we just basically check this. Is this less than the nth term? And I think that that's fairly obvious because we're adding 1 to the denominator here inside these parentheses, which definitely makes this less than that. So that's a check also. So this thing converges by alternating series test. For part E, we're going to notice that this is actually also an alternating series. Just remember that when you see cosine n pi like that, that is exactly the same thing as if you have negative 1 to the power of n. You can verify that by plugging in a few values of n. And then we clearly see that we have an alternating series, so we want to check the limit as n is infinity of 1 over e to the n. And that is clearly 0. And then we also want to verify that 1 over e to the n plus 1 is less than 1 over e to the n. And again, I think that's obviously true. So this is a check as well. So series converges. by the alternating series test. For part G, we'll notice that even though it says in the practice exam that we can use the integral test here, direct comparison is actually easier. We can notice that, well, if we compare this to this one, start it at 2, 1 over n, which as we know is a divergent p-series. Then we can compare ln n over n. How does that compare to 1 over n? And I think it's fairly obvious that it is greater. So, because we have an ln n there. And this is greater really for n greater than or equal to 2 only. But that is really all that matters since we're starting at 2 for this series anyway. So since it's greater than a divergent series, then it must diverge. So we say it diverges by direct comparison.